Okay. So you just feel that in last class we had discussed up till what is a solenoid. A solenoid is an arrangement of closely wound, copper wire which are insulated, right? And the funda of a solenoid is that the length of the solenoid, now we will take some time to understand that also. When you say length of the solenoid and length of the wire, so let's first understand these two concepts, then automatically the rest will also become easy for you. Okay, so let's say cylinder, I don't know. That's stitching thread you have seen, right? The thread which we I think it is better I do it without this. Easy. 1 minute, children. Just 1 minute. So you understand that this is some sort of, if you see that coil which is there, the keyring coil, that's like a solenoid. Okay. Now, I can't coil on just leave it in the atmosphere. So what we think, imagine that this is a small piece of a PVC pipe, or like the sewing thread which we have. The thread is always wound on what? On a piece of cardboard. Let's say this is the cardboard, right? And your solenoid is something like, let's change colors. Your solenoid is like wires which are wound in this manner. This is one end, and let's say this is one more end. Have you understood? This is a solenoid. So if you see it from another end, it's like circular coils like this. These are the circular coils, right? So one of the things that we have is like, say this is the radius of the coil. This is the radius of the coil. In a solenoid, there are two things. One is, we don't call by length of the wire. We say length of the solenoid. Have you understood? The length of the solenoid is from here to here. Got it? Let's say the length of the solenoid. The length of the solenoid is, say, length is equal to L is the length, right? And let's say N is the number of turns. N is the number of turns that you have put out here, right? So in a solenoid, the length is much more than as compared to the radius. So the radius of a solenoid does not have any importance as such, and the number of turns is very high, huge number of turns. We have another something called N. N is equal to number of turns per unit length. Now just see this thing. What is the length of the solenoid, beta? N. In N, how many, sorry, L. In L, how many turns did you give? Capital N. Try to understand. So your N value becomes what? Your N value becomes number of turns per unit length. So your N, number of turns, is equal to NL. Have you understood this? N is the total number of turns. L is the length over which the turns are spread. So if somebody tells you per unit, suppose this is in 1 meter, I have got, say, 100 turns. So so in 10 meters, I have got, say, 100 turns. So in 1 meter, how many turns do you have? So you will be doing in 10 meters, so many turns. In 1 meter. So this is what we understand as. Is this clear now? Yeah. Okay. Now some more visualizations we will need. So let's take this solenoid now and cut this solenoid in the longitudinal manner. You just cut it across. So if you cut it across, what will you get? You will get a half pipe. But the cross section, I'm drawing the cross section in this manner. This is, say, the top portion of my cardboard, and this is the bottom portion of my cardboard. Okay, don't get prejudiced by your book. This is a pipe. This is a pipe. I've cut it. The pipe has a thickness. So this is the top thickness. This is the bottom thickness. And on the back side, have you understood? You have just cut it across. The thickness has been, and the wire is actually, the wires are like this. See, the turns are like a half bangle on this side, a half bangle on the back, half bangle here, half bangle there. Are you able to visualize? As of now, I'm in this drawing, I'm not drawing the wires. I'm just saying that there will be, don't you think that there will be some protrusions from where wires are actually coming out? These are the protrusions from where wires are coming out. The wires are coming out. Are you able to understand? So that means the half bangle is like this and the half bangle is on that side. Now let's say the wire is coming out in such a manner that I'm assuming that my current is going like this, then again it is coming out, again going like this, again going like this, again going like this, 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 this. Have you understood? So if you look at the top portion, the current is actually going inside. Half current is going, and the current is coming out from the bottom portion. Okay? So I am making this is a current diagram. My current diagrams are like this. Current is coming out from these holes, or these are the wires where the current is coming out, and the current is going in this manner. Children, have you understood this part or not? Just tell me. Clear? Okay, now is the interesting part. So you have understood from wires perspective. So based on your drawing that is there in the NCERT drawing, now I'm completing the NCERT drawing. It's very like a hydra. Fair enough? Clear? The same is put out here. Now I will not be concentrating on, if I start making these circles, my diagram will become a little bit distorted. So what I'm saying, I'll just keep the dots, okay? Okay, leave this. This one will help us anyway. Okay, now have a look. So wire is coming out. Now let's apply our right hand thumb rule. Here the current is going inside. So on the first wire, applying right hand thumb rule, I'm making it like this. See, the wire is it's going inside. So the magnetic field is like this. This is the yellow is the magnetic field diagram. Current is going inside. Okay? So if you see the second one, then also what will happen? Okay, I'm going to make them a little bit smaller. Are the top ones clear with you? Let's look at the bottom one. Current is coming out. Current is coming out. So if the current comes out, is it understood now? And just for simplicity purpose, I am keeping one wire or two wires just for your demo purpose. Okay, now try to visualize the thing. Okay, let's see the top portion. On the top portion, this is like this. This is the bottom portion. So if you see the top one, then the current is going inside. So you have this, 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 this. Sorry, here it will be reverse. So here it will be this and this, this and this. Now see, this is what I lost track the other day. Now if you look inside the solenoid, now please understand these are all vacant. I have got wires which are actually curled in this manner. When I call inside the solenoid, I have made a magnetic field diagram out here, but the wire is continuously coming till here. So this circle will be in every portion of this wire. Here the wire is perpendicular, here the wire is perpendicular, here the wire is turning. Are you able to visualize? The circle is always perpendicular to the wire. So it's like a bangle which is coming out, then the bangle will become horizontal, again the bangle will go inside. In each of these diagrams, if you see in the inside part, okay, if you see in the inside part, now our solenoid is on this side. So on the inside part, there will be uniform magnetic field. Our magnetic field will be uniform, and above that, they will be in one direction. So they will be in one direction and they will be uniform. The magnetic field is uniform inside a solenoid. Now just let us see. If you see these arrows are all pointing this side, this side, this side, this side, this side, and these arrows are all pointing this, this, this. So the magnetic field is actually acting on this side. Are you able to understand? In your book, the magnetic field might be on this side because in their case, current must be coming out from this side and going in from that side. That's just a convention. So our diagram has come on this side. So all the wires are contributing magnetic field only on the inside of the solenoid. Now what is happening on outside? If you see, the wire is on this much portion. See, my wire is on this much portion, this. Anything that is external to the wire, you are having a formation like this. This is what we say that the opposite magnetic field, anything in the exteriors are getting cancelled out. And you have to have a bit of visualization. The wire is like this. The yellow circle is not limited here. The yellow circle is along the wire. So everywhere the yellow circle is outside the wire, the magnetic fields are getting cancelled, and inside they're all in one direction. Are you now able to appreciate that? This is a piece of wire. How do I? Yeah, I have it. So let's say let's try and make a solenoid loop out here. Okay, so understand, just appreciate that this is like a solenoid now. This is a solenoid which is wound around some body. Okay, so as much as it supports us, we can have it. Now you have, this is what is the scenario now. Coil 1, coil 2, this one. The yellow circle is passing all through it. Yeah, I am doing a diagram here and here. But every time two yellow circles are there, the outside is getting cancelled. You are having this formation, see. But then inside it is uniform, and is it in a straight line parallel to the axis. So you can write down that the magnetic field inside a solenoid, this is very important. Magnetic field inside a solenoid, due to each turn, and please understand, look, for this wire, let's say this is wire number 1, it will create a magnetic field B1. This will be wire number 2, B2, B3. All magnetic fields undergo superposition theorem. So all the magnetic fields due to each of the turn add up inside the wire and ultimately are in the same straight line. So you can write, they add together inside a solenoid and create a uniform magnetic field whose direction is parallel to the axis of the solenoid. They create a uniform magnetic field whose direction is parallel to the axis of a solenoid. And that's why the solenoid is going to behave as a bar magnet now. Okay. And write another paragraph. Now on the outside of a solenoid, magnetic field produced by one loop is opposite to the magnetic field produced by the neighboring loop. Magnetic field produced by one loop is opposite to the magnetic field produced by the neighboring loop, and as such cancels each other. Therefore, magnetic field outside the solenoid is taken as 0, is taken as almost to be 0. It isn't exactly 0, but for derivation we take it almost as 0. Magnetic field outside a solenoid is taken as 0. Okay, children, once again, now just see this once again. The solenoid has got turns like this. All these are turns of the solenoid, okay? Turns in this manner. And this is how the best I can make you visualize the turns. These are the turns of the solenoid. These are the turns of the solenoid. Now, when you are trying to see this diagram is actually trying to show you each of these turns which are outside. You're seeing only this much portion. The other portion is behind, which is not drawn. Again, you see the outside one. Now, the magnetic field out here in my diagram, the current is going in. So the magnetic field will be in what direction? Like this. So if you see, it's in this direction. See here, it's in this direction, right? Then if I see at this position, that is the curve is, let's say the solenoid curve is like this. Oh, this one also doesn't. Yeah, let's see in this direction. This is half of a curve, half of a curve. This. At this portion, this is the direction. Then as you are coming in the middle part, the current is like this, like this, like this. And as I'm coming at the bottom, the current is like this. Satisfied now? No, internally the direction is coming straight. See, this one is pulling in this direction. This one is also pulling in. It's not about cancelling. It's like this. If you see the internal portion of the top loop, say loop number 1, there's an arrow here, there's an arrow here. This is B1T, B1 top, B2 top, B3 top. If you vector add it, all are in this direction. And then this is bottom. Bottom one is here. This is also here. This is also here. This is also here. Inside, see, the whole space of a solenoid is hollow. When you say inside means only this much portion, only this much portion, because you cannot imagine that the cardboard that you are trying to think. I mean, I'm not getting anything round. Well, which one? That is the best example of a solenoid. Okay. Now see. This is your solenoid. The best way we this is your solenoid. There is nothing inside. You are seeing only this half portion. This half portion. There's a circle, circle, circle. The circles are continuously forming here. So only on the inside means this bottom portion of the wire. Outside means top portion of the wire. On every top portion, two circles will cancel each other. On every inside portion, two circles will move in same direction. Is this clear? Now, okay. So now we have to find out what is the magnetic field along at a point on the axis of a solenoid. We have to find out what is the magnetic field at a point on the axis of a solenoid. So I'll draw my diagram once again, the same diagram that we have drawn so far. And so let us say this time I'm making my thickness very small. Okay. And this is my solenoid's thickness. Okay. And this time I'm taking my magnetic field in this direction. Okay, let's take the axis first. This is my axis. I want to find out the magnetic field at a point on the axis of a solenoid. So I need to find out the magnetic field lines. The magnetic field lines are always uniform and constant. So they will be parallel lines. These are the magnetic field lines. And you want to find out the magnetic field intensity at a point on the axis. Let this be the point. Let P be our point, and we want to find out what is the magnetic field intensity at this point. Fine. In order to calculate the magnetic field intensity out here, we will consider Ampere's circuital law. So we will go for an Amperian loop, and this time the Amperian loop that we select is a rectangle. The Amperian loop that we are selecting is a rectangle. Let's say this be our Amperian loop. Okay. This is the magnetic field, which is constant and uniform. And you have selected an Amperian loop. And your Amperian loop is such that it is A, B, C, D. So we have selected a Amperian loop. Our Amperian loop is a rectangle A, B, C, D. Half is inside the solenoid, half is outside the solenoid. Okay. And half outside. Where we have taken the length of AB to be equal to L. We have taken the length of AB to be equal to L, H, kuch bhi le lo. L is the length of the loop. Okay. Now we apply Ampere's circuital law. So in Ampere's circuital law, what all we have to do? Surface integral B dot dl, right? So we have to take a B dot dl, and this is taken for entire what? ABCD. Can I not write this as that this is the surface integral of AB? We will do a B dot dl. Then we will do surface integral of BC, B dot dl. Then I'll do a surface integral of CD, B dot dl. and then I'll do a surface integral of dA for B dot dl. Sir, why are you not mentioning it in vector format? Because my job is to find the intensity of the magnetic field. Did you understand this? B dot dl over the entire loop is doing B dot dl integration. We can split up, right? B dot dl. Now look at some interesting part. Look at some interesting part. dl, okay, dl. Now B is going in this side and I am taking AB. So my dl is also, dl is an element, not current element, element of the Amperian loop. So the dl vector is also on this side. So if you look at BC, then your B is in this direction, dl is in this direction. For this, can I not say theta is equal to 90 degree, children? Theta is equal to 90 degree for the BC. So if theta is equal to 90 degree, finally this value should be equal to 0. This BC component of this should become 0. Do you agree or not? And the same story will happen for dA also. Here also theta is equal to 0, 90 degree, as a result of which the surface integral of dA should be equal to 0. So, in other terms, I can say that this fellow does not contribute, this fellow does not contribute at all. Is the explanation understood by you? Okay. Now something interesting is happening on this part. Let's look about CD. In CD, B is equal to 0 because this is the exterior of the solenoid. There is no magnetic field, which means our fellow B dot dl for CD also does not contribute at all. Clear? So who is the one who is only contributing to you? BDL AB is contributing to you. Shall we? So let's solve this. So finally, this whole thing, integral B dot dl for the entire Amperian loop ABCD finally is equal to integral of only AB for B dot dl. And I can write B is constant. I said that the magnetic field inside a solenoid is constant and uniform, and dl is equal to L because you have already assumed that the length of AB is equal to L. This was assumed by us. Do you agree or not? Clear? Now come back to Ampere's circuital law. It tells me that closed surface integral, closed loop B dot dl should be equal to mu naught times the current enclosed. Mu naught times the current enclosed. That means B into L is equal to mu naught times what? Current enclosed. Mu naught times the current enclosed. Now our job is to see what is the current enclosed. Now see, what is the length out here? L. And what is the number of, N is the number of turns per unit length. Each turn is contributing a current I. My job will be, what is the total, how much current is enclosed here, will be given by how many loops you have enclosed here. And what is the small n? Small n tells you how many turns per unit length. Small n was always number of turns per unit length. And now my chosen length is how much? L. If you have a confusion, children, you can take this as H also, your wish. See, in the previous example, don't confuse. This L means if the total length. So if you're getting confused between the two L, you can take this as H also. Okay. N turns per unit length. How much length does the Ampere loop consume? L. So how many turns are inside it? NL. So effective turns inside the Amperian loop should be equal to NL. Ajay, did you understand this logic or not? Sir, how many total number of turns your solenoid has? I will say my solenoid is a infinitely long solenoid. I don't know how many total number of turns are there, but I know that this solenoid's turn density is small n, means per unit length the number of turns are small n. How much length are you eating up now? L. So how many turns did you consume? NL. Each turn has got how much current, Zoe? I. So NL turns have got NLI. So B into L becomes equal to mu naught. This I enclosed becomes NL I, where I is the current carried by a solenoid. So initially when you are deriving, you can actually write, let us consider a solenoid. Actually, you will write that line right at the top of your derivation. That the derivation considers a solenoid of infinite length. The derivation considers a solenoid of infinite length with, number one, number of turns per unit length equal to small n. The derivation considers a solenoid of infinite length with, number one, the number of turns per unit length is equal to small n. Each turn carries a current I, capital I. Each turn carries a current, capital I. Correct? P is a point on the axis of the solenoid. P is a point on the axis of the solenoid. And we are deriving to find out the magnetic field strength at the point P. Now, I think it makes you clear. And we are deriving an expression that helps us evaluate or estimate the magnetic field at a point P. ठीक है बच्चा? एक infinitely long solenoid ले लिया, जिसमें कितने number of turns है हमें नहीं पता, but number of turns per unit length is small n. Each turn is carrying a current I. You have considered a point P at the center of the axis of the solenoid, and your job is to find out what is the magnetic field here. So what was your analogy? You said that when you see this solenoid and you see a cross section of the solenoid, so you all see is half loops out here. So current must be coming out from one and going in another. Based on the right hand thumb rule, you have drawn some loops everywhere where the current is coming out, and you find that the loops only contribute for a magnetic field in the inside of the solenoid, and the outside, each adjacent loops are having opposite direction, so there is no net magnetic field in the exterior of a solenoid. Further, once you have established that, you take your point P and you consider an Amperian loop, which is a rectangle, such that it is half inside the solenoid and half outside, and then you apply the closed loop integral over the four arms of the rectangle, in which you find that these two arms are exactly perpendicular to the magnetic field. As a result, they cannot contribute, so it's 0. And same is with CD, though it is along the or opposite to the magnetic field. The problem out here is this exterior, and exterior does not have any magnetic field as per our already considered assumption. So it's only AB. So when we look at AB, we find that if we integrate DL, it gives me the length. So how many number of turns come here effectively? N per unit length, so NL. The total current that you are carrying is NLI. And from here, L and L cancel each other. So B becomes equals to mu naught NI. This is the, sorry, the N will be small n. So the N will be small n. And if you want to actually put a capital N, then you will put a capital N by length of the solenoid. समझ में आया बच्चा? Right, very good. So can you please note down two more things out here? You found out the magnetic field due to a wire and due to a solenoid, both by Ampere's circuital law. So let's just compare both. Okay. And before we compare, one more thing. You look at this expression. Now you tell me, if you are given an opportunity to increase the magnetic field, what are the parameters you will tweak? Tell me. If you want to increase the magnetic field, what is the parameter you will tweak? Current and turns. That's what you learned in grade 9. Double the turns, double magnetic field. Double the current, double. So if you get a question, like yesterday we were seeing the relaxation time. If you see a question, if the current is doubled in a solenoid, what happens to the magnetic field? Doubled. If the turns are doubled, doubled. Got it? Okay. So let's see a small comparison between the magnetic field due to wire versus solenoid. Wire versus solenoid. If you remember this, even if you don't remember, just see infinite long wire. Look here. It's an infinite long wire and there is a point P. If this distance is R, then the Amperian loop is actually a bangle around it. Then what should be B dot dl? B into 2 pi R. And on top side, what did we get? We got mu naught N I divided by 2 pi R. It was mu naught I is for a single. Here we want, why am I putting N? N comes only when you have a solenoid. This is mu naught I. This is very easy. If you have forgotten, just remember like this: one wire, and this is a point P. The distance to this point P is R. Amperian loop is a circle. So if you do BDL, what is BDL's value? B into 2 pi R. And that should be equal to mu naught into the current enclosed I. So B is this. Here, what did you find? B is equal to mu naught N I. So straight away you can see that the magnetic field intensity is much more in a solenoid. Okay. About field lines, we will have circular field lines. And here we will have straight uniform lines parallel to the axis. These are circular field lines. Here we will get circular field lines like this, like this. On that we will be getting straight lines. Which one? Yeah, closed loops. Which one? Inside, exterior there is no more loop. Inside is all solid. Okay, next. Outside field exists. Here there is an outside field. Outside field exists. And here we will say no outside field. No outside field. Outside field does not exist. Here, next point, field decreases with distance. Obviously, here field is constant and uniform inside the solenoid. If you move away, R increases, field reduces. Here the field is always constant. Solenoid. All we are interested is like this. Whenever you have a doubt, the solenoid's important part is only the inside of the solenoid. This part.
Said that the field just in the solenoid is half.
Which one?
Like he said that on the midpoint of this side of the solenoid.
Outside, if you come outside the solenoid. Where? In school. In the solenoid, inside of a solenoid, the magnetic field is always uniform. It's not half, it's constant. That's the basis. That's why you took B as constant in the integration. If you come out, see, my diagram is not that accurate. From which point? Here it should not be like this. This portion is actually not correct in my diagram. This portion, it should actually now from here divert out like this. It's not half, it's taken as almost zero. There's nothing called half. There won't be any solenoid. If it is half, then you should not have taken this integral as 0. Does not exist. Solenoids, first thing is, the assumption is it almost cancels. It's not that there won't be any magnetic effect out there. There will be, but that is taken as 0. That is non-comparable as compared to the intensity inside. So our job of our concentration is only from here to here. This is our solenoid, not beyond that. And further, you will learn that you actually put a soft iron core inside for more concentration. That's the other part, that the magnetic field can be also increased by putting a soft iron core, where you are actually playing that time on mu naught. Right now it is assumed to be vacuum. Okay? All clear? Okay. Moving to our next section. Our next section is force between two current carrying wires. Two current carrying wires, and from here we will get the definition of, we had one numerical in between, but I'd like to finish this one first. So our next topic is force between two current carrying parallel wires, and this actually combines Biot-Savart law, Ampere's law, and Lorentz force, everything. This will give you the definition of the ampere. How do you define the ampere, which was taken up to be the SI unit from 2019. Okay, so let's take two current carrying conductors. See, this is one current carrying conductor. Two parallel current carrying conductors. Okay, two parallel current carrying conductors, and I'll make the axis of them. This is the axis of one, and this is the axis of the other one. And let's say that the distance between the two wires is D. Two parallel wires maintained at a distance D, and you are feeding current to both. So I'm feeding a current, say IA and IB. This is my wire A and this is my wire B. So you can write as you draw. Two parallel wires A and B are taken. Two parallel wires A and B, separated by a distance D, are fed with currents IA and IB respectively. IA and IB respectively. This is very interesting derivation. Two parallel wires, see, two parallel wires A and B are separated by a distance D, current IA and IB, and these two currents should be steady currents, okay? Current IA and IB are fed through the wires A and B. Is the assumption part, have you written? Now look at the diagram, so it becomes clear. Two current carrying wires, two current carrying parallel wires, separated by a distance D. One wire is A, one wire is B. Current flowing through A is called IA, current flowing through B is called IB. Clear? Now, first thing, point number one. Does wire A create a magnetic field? Ask yourself, does wire A create a magnetic field? Yes. Current carrying wire creates a magnetic field. Any doubt about it? No doubt about it. Now let's say you consider, just for your assumption part, huh, children? Now we want to find out what is the magnetic field at a distance D from this wire. So though that is not required in our diagram, but I'm still drawing. My Amperian loop would be a circle like this. My Amperian loop would be a circle like this. what is the, forget this wire now, at a distance d from this wire, what is the magnetic field? Mu naught I by 2 pi d. Just now we did. It's the same thing. This distance is now d, correct? So can I write create a magnetic field? My answer would be yes. And this magnetic field is the magnetic field created due to A, and this magnetic field will be given by mu naught I A divided by 2 pi into D. Think, children. Is this clear or not? No doubt? Now bring your focus to wire B. Now bring your focus to wire B. Is B carrying a current with it? Yes. So is B also a magnetic substance? Yes. So does he sense this magnetic field which was created here, right? The magnetic field was created at this point. So let's find out the direction also. Let's find the direction. Current is going in this direction. So the magnetic field is getting inside this axis. Do you agree? So here I have a magnetic field like this, and this magnetic field is the BA magnetic field. Clear? BA magnetic field. And what is the direction of BA? BA's direction is going inside Remember that. BA is going inside. Fine. Wire B, okay, experiences BA and thus will experience a magnetic force. Wire B will be experiencing a magnetic force. Do you agree or not? Yes, wire B will experience a magnetic force. Now here, what is the concept we will be bringing? What is the concept we will be bringing? If you try to remember, the magnetic force is equal to I L cross B. You have read this formula, I L cross B, where L is the length of a conductor and I is the current flowing through the conductor, and B is the magnetic field that the conductor is sensing. Now put that story out here. My poor little wire B is now sensing this magnetic field which is created by A. So the magnetic force that your wire B will be created, magnetic force on B due to A. Force on B due to A. Why due to A? Because if A was not there, the magnetic field wouldn't be created. Now you can say, sir, I am also a wire, I am also a magnet. Good. You are a magnet. How do you feel your magnetism? You being a magnetic substance, you will feel another's magnetic effect. Is this clear or not? As long as you are the Dada, you are the Dada of one territory, how does it bother you? There is another Dada who has come here, now you sense it. Yeah, please, go ahead. Field, yeah. I'm considering only A. In A, the current is going in this direction. See how the current is fed? The current is going in this direction, my thumb. And I curl my finger. So if I curl my finger, the magnetic field here is inside. Wasn't going? Yeah, going inside was a cross. Okay, oh, that one, yes. Going inside was a cross. Pretty good. So the magnetic field is going inside. Thank you for that correction. Is this fine? Now let us put this for, I'm saying that force is FBA. And this FBA force should be now equal to, this is the current that B is carrying, IB, right? Let us assume a small length element L out here. This is an infinitely long parallel wire and I am assuming a small length L. End of the day, this L will go away. Multiplied by the B means L vector crosses with BA vector. BA because the magnetic field is BA. If you have understood this, you have understood Ampere's law, you will be able to find out the Ampere definition. Is this thing clear now? Okay, very good. That means B experiences a force. Now it's time for us to understand how the force will be acting on B. Now wait. L cross B. What is L's direction? L is a current element always in the direction of the current. So L is going in this way. B is going inside. B is going inside. B is going inside. And L cross B is actually a vector which will be parallel to both, perpendicular to both L and B. Getting a little bit difficult? Why are you thinking that way? Go back to grade 10. Fleming's left-hand rule. Fleming's left-hand rule. FBI. B is going inside. B is going inside. B is going inside. I is going in this direction. Where is my thumb pointing? Upwards. So that means if this wire is up, my B wire will be facing a pull now, and the pull is along this side. This is the pull. So this is my FBA. FBA. I'll go to the derivation later. Now just swap the story. Like you make him the victim. Think that B is out here. B is out here. And B current is going in which direction? This direction. Again, the rule becomes the same. Curl your fingers. So if I want to find out at a D distance here, considering this wire, this is the current carrying wire, then the magnetic field here will be coming out. Got it? So I can also say that there will be a magnetic field here which is BB, and this magnetic field will be in this direction, and current is going in this direction. That means for him the attraction will be downwards, which actually tells you that if a magnetic force FAB will be just opposite to FBA, and this is actually honoring the action-reaction pair of Newton's third law also. This is to every action. Now see, what is Newton's third law? If a body exerts a force on another body, the other body should exert an equal and opposite force on the other body, both forces being categorized as an action-reaction pair, and Newton's third law is also established. Okay? So can we now go from here and find our derivation? Okay, so I'm making this little bit smaller so that I don't change. Whoa. I don't change. Many things will go away. Yeah, let them go away. Don't mind it. Okay, so we have FAB as a force is negative of FBA as a force. Okay, fine, children. Now, FBA, I'm just writing what we wrote, and I'm concerned only about finding the definition of amperes. So this is IB into L cross BA. So I'm now writing it as L into BA, because the theta here is 90 degree and sine 90 is equal to 1. So L cross BA. And sine 90 was needed by me only to get the direction of FBA. Is this understood? So let's go further. I bring out FBA and I bring the L on this side, and I call this as some force F. What is this force? This is the force per unit length. Force per unit length on the wire. And in our case we are doing for say wire B. Ultimately it is actually telling you for both. So the better way to write it would be like this. This is same as written as F upon L, which is F. Did you understand this? While we are doing our problem with FBA, and FAB is also same. So ultimately it's a force on a conductor, whether you are considering from this point of view or this point of view. Clear? And that F by L is a small f force, which is force per unit length. That is what we want to find out. And let's put our definitions now. Okay, what did we find out? BA's value as mu naught IA, clear? And then IB, L is already gone. Mu naught IA IB divided by 2 pi D. This is a very important derivation which will tell you the definition of ampere. Now, if you take, if IA is equal to IB is equal to 1 ampere, D is taken to be 1 meter, mu naught you know the value, then you actually find out that F, which is equal to F by L, this comes as 2 into 10 to the power minus 7 Newton per meter. You can do it. Mu naught by 4 pi is 10 to the power 7. So mu naught is 4 pi into 10 to the power 7. If we solve this, now are we in a position to define what is 1 ampere from this definition? 1 ampere. 1 ampere is defined as, first listen, I may be wrong grammatically. So let me first go by 1 or 2 iteration. 1 ampere is defined as the strength of the steady current, which when allowed to flow through two parallel infinitely long straight wires separated by a distance of 1 meter, makes them experience a force of 2 into 10 to the power minus 7 Newton per unit length, when placed in vacuum. That's why we are, see, you have to honor everyone. Physics definition is not about going by English. You have to honor everyone. So once again, looking at the diagram, 1 ampere is the strength of that steady current, which when flowing through two infinitely long parallel straight wires placed in vacuum, makes them experience a force of 2 into 10 to the power minus 7, or creates a force of attraction. See, the other force will be on this side. So better word will be creates a force of attraction of 2 into 10 to the power minus 7 Newton per unit length. अब आप लिख पाएंगे. And one more thing, if somebody asks you, why do parallel currents create attractive force? Because in parallel currents, current direction will be here. However, for this wire, the magnetic field will be inside. For this wire, the magnetic field will be outside. So if you apply Fleming's law, or if you do L cross IB or L cross IA, once you will get the force on this direction, once on this direction. If the currents were reversed, there will be a repulsion. So can we define once again? 1 ampere is defined as the strength of the steady current, which when flowing through two infinitely long straight wires placed in vacuum, creates a force of attraction of 2 into 10 to the power minus 7 Newton per unit length amongst them. And if you can better it, you can better it, but at least after writing, read it, what you have written. Force of attraction, or since you have written same direction, so it is force of attraction. वन एम्पियर किसे कहते हैं? 1 एम्पियर वो स्टेडी करंट है जो दो सीधी अनंत तक लंबी समानांतरी वायर्स. अच्छा, we didn't add the word separated by a distance of 1 meter. I think that was missing. Check your definition. You can't leave out the 1 meter. 1 ampere is defined as the value of the steady current which when flowing through two straight infinitely long wires placed in vacuum at a distance of 1 meter creates a force of attraction of 2 into 10 to the power minus 7 Newton per meter between them. I think it's clear now. Perfect. I won't sleep from that last class then, because once things doesn't go well. Have you understood now how the amperes definition comes? Our next thing will be force experienced by a current carrying wire placed in a magnetic field, which is actually the birth of motor. Why does the motor rotate? A motor will have an external magnetic field. So in your grade 10 also I said, this is, now you remove this wire. You just take this wire. Is this wire carrying current? Yes. Is this wire a magnet? Yes. Now put this wire in another environment where there is an external magnetic field, which can be either due to an external magnet or due to an electromagnet. Hungry boy placed near a sweet shop. Do you feel that there should be something? Two things might happen. He might go and taste the sweet and say, hey, what nonsense. Either he'll repel out or he'll keep on eating. But one thing which you cannot rule out is the interaction. A hungry boy placed in a near a sweet shop, 100% there will be an attraction or a repulsion. That we don't know. So you usually will say, like last year my grade 10 kiddo said, sir, attraction. How do you know there will be attraction? He may just taste something and say, cha, I don't eat it. Like if somebody gives me a baklava, I will never eat again and go to that shop. Because I don't like that sweet. But that doesn't rule out that I will not have an interaction. I'll definitely go there. Or else I will fall in love. Some good rasmalais are available. So you go on eating. So that's our next story. That actually will tell you why the motor rotates. So once that is done, we have, I think, a galvanometer, moving coil galvanometer, then we will be able to end. Because these formulas will be used in electromagnetic induction. After that, now slowly it will become easy, except the next chapter, which is very, very theoristic. Ferro, paramagnetic, and all. Have you understood today properly? Good. Is your solenoid funda clear? Very good. And your ampere funda clear? I'm sorry we could not do two problems, which we'll do in our next class. Don't worry.